For the last 8 episodes on Low to High Level, we've been doing a lot, but all of our work has been in hardware, designing a custom CPU or central processing unit and building an emulator for that. In the last video, we took some binary data, so we wrote machine code to print hi to the screen. Now that's great and all, but let's move up a layer of abstraction. Instead of writing machine code, we can write what is called assembly code. Assembly code is a programming language that is specific to the computer that we're dealing with, and it converts directly our instructions that we write to machine code. It's a one-to-one comparison. It's not anything fancy like any high-level programming language like C, but it's a good step up. And that means we can move into what is called the firmware level. So it's code that we write that connects directly to our computer. So that's what our goal will be for the next few episodes, dealing with this firmware level of code. And from there, we can move on to either better hardware or better software, but this will be a key to understand how we can write some software. So let's get started.
Here we are in my terminal. Here I can run a few commands. So I can make a directory, and let's give it a name. How about ASM video? That could work. So if we go into this directory, we have plenty of things we can do. This is where we're going to write our code in assembly. So let's create a quick GitHub repository so we can do a few things. So assembly files have a few different names that they could have. And for our case, we can use either .s or we can use .asm. I'm going to prefer to use .s. So let's create a main.s. So editing that file, we can do plenty of things. Last time we wrote a quick program that does some minor things and prints to the screen. Let's recreate that as it was. We can print to address 16 through 84. That is our general output address. So let's load that into register 1. From there, we can do a few things. Let's load in register 2 a letter like H. And to output it, we will write at the address of R1, R2. This will print to our screen. If I copy and paste this a few times, we can eventually write a program. So if I replace the characters with an I and an exclamation mark, we can do that. If I use \n, that basically means that I have an output and it's a new line. So that's great. Here we're going to load to register 30 the value 36,000. This is a little hack with our emulator that allows us to output some data. It's nothing crazy, just lets us close our program since we don't really have a way to turn off the computer as of right now. Creating a file called makefile will allow us to do what we need to create this stuff easily. It's a special format that is used for GNU Make, which allows us to just create whatever we want easily. If I write phony and then a couple of things, we can create a couple quick programs that do things. For example, we'll have a.out, which will have an input file of main.s. And if we put a tab after the new line, we can write some commands that will create it. We will make the previous directory and ASM, which is our assembler, just so we make sure that this will work. This does require a certain folder path, but that's fine. So if we run our assembler with -s2, which is our second stage of the emulator, and then we give it our input file, which is main.s. This will allow us to build our a.out. Our all output will just run clean and then a.out. So let's make a couple other things. Clean should remove our a.out file, which is our original output. So that -f there just basically means that we are force deleting it if it doesn't already exist. And then we can have run. And this will depend on a.out. So we will make in the previous directory our CPU file, and we will run our emulator, which is in CPU/target/. target/emu, and then we will have -r as an argument, meaning we will do registers. And we could have -f, but instead we're just going to do that because a.out in the current directory is the default. So that should be our makefile. If I run nix-shell in the CPU directory, this just gets me into an environment where I can compile our assembler and our emulator, so things will run. It'll also allow for our makefiles to run. Now that we're back in this directory, we can run make. And we see an issue here. So let's figure out what that is. Some quick debugging looking at our makefile, which is where our issue is. You can see right here at phony, we need a colon. That should be it. So now let's run make again. And we do not have a such file or directory. This is because we need to type -c to actually run make in that directory. Now we can run make, and this should have built everything successfully. Looking at our file, we can see that it's a bunch of jarbled mess, which means we are good. Now let's run our program. Looking at a bunch of registers, we see that it printed high, and that's exactly what we want to see. Labels are a nice feature of assemblers, which lets me type init colon and type some sort of load, like loading into register 30, some value like 14,332. This is based on our outputs, and this will set our stack pointer. Then we could do something like a jump, and let's jump to main. Now, main can be a new label, and this will be our main program. We can then write some comments to just kind of explain what's going on. So this will initialize the CPU and the init function and set up our stack, and then we'll go into the main function, which will be our main program. Let's test it. We can see that we've made a few changes, and it still prints high. That is great. Now, all of these prints that we're doing are very manual. It would be nice to be able to break this out into a function so we could reuse it in the future and add another layer of abstraction. So, let's do that. You can see that we do jumps normally, but we can do something a little better. That's more of a pseudo instruction or fake instruction that we have. So let's create a function and call it print char. So I like to give a title to or a description of my functions and then say what registers I'm using. So in R2, that will be the character that we are printing. After that, we can use some sort of pseudo instruction that our assembler makes, but isn't a real instruction in our CPU. In that case, we have call and we have ret. Ret is going to be the one that we will use, and it requires a register, so we'll use R26. So let's do that. Let's load into R2 the value that we want to print and call print char. This will load our output register, and then it will print rs1 at the address of R1, R2. We won't need R1 in the other place, and we won't need to write anymore. We will just load our value and then run call print char. We'll do the same for the rest of these. Awesome. Now let's test it by running make run. Scrolling up, we see that it still prints high. Unfortunately, there's a little issue. This 16384 really shouldn't be here. To prove that, we need to store and reload this value. Let's show it by loading into R1 some value like 15. Running that, it's overwritten with 16384. Now, that's not very nice or useful for us, especially if we need to run a lot of functions. We can overcome this by writing R1 to the stack. At that point, it'll save what it is before, and we can do a few things afterwards. For example, let's update the stack. Once you write to a stack pointer, what if you need to reuse it? So we can subtract from R30 the value in R30 and the value in R28. The way our call function works is it adds 4 to R28 and just overwrites it. So this will just make it a little easier. At the end, we do something similar. So let's copy and paste this. And instead of subtracting, we are adding. And instead of writing, we are reading. But we should add before we read because we are subtracting after. So this should just make everything work and run flawlessly. We can test our function and see that R1 is now 15 and we still print high. That's great. Now, it's a pain to have all these functions in one file, so we can split it into multiple files. Let's add io.s to our makefile dependencies, so we are checking that whenever we build, and let's create that file. Now we can cut and paste our function to the new file. In our main function, we can use a special instruction called include, which just says that we are including this io.s file. Let's test it. It seems that everything seems to build, so let's give it a run. And everything works exactly the same, and we still print high. Awesome.
So as you can see, writing in assembly is a lot more powerful than just writing in pure machine code. It allows us to abstract things a little more than we could in just pure bytes. And though it may add a couple instructions extra here, it makes things a lot simpler for us to understand and write as we go. That'll be it for this episode. If you really liked it, be sure to love it. Give it a like, and if you really loved it, make sure to subscribe. In the next episode, we're gonna dig a little deeper into some assembly programming and look at a few little math functions that we can write. All right, bye.